So this is lecture 15 for mae3060. This is for 29th October 2014. Last time we talked about reference frames. I'll talk about them again because we touched on all this material a little bit at the beginning of the semester. We talked about the angular velocity. We defined it as a vector that relates two frames. So it's the rotation of one reference frame relative to another reference frame. And we can embed those reference frames or fix them to bodies, or we can affix them to inertial space. And in doing so, we can talk about the angular velocity of a body relative to some inertial frame. But really, strictly speaking, it's a mathematical relationship between, or even among, frames of reference. We also talked about the motion of a boresight, which we called p. The vector p is a unit vector. We talked about the motion of it as just a stationary thing, p, the position or direction that, let's say, a sensor is pointed. We also talked about the velocity of that boresight, so that's p's derivative in n, and we write that with a little kind of over dot over the vector. We indicate the reference frame by putting the letter of the reference frame, in this case n, over that vector. So rather than saying p dot, it's p with a little n over it. And for us, n indicates the Newtonian or inertial frame. And we talked about the acceleration of that same vector, so in that case it's p with two n's over the top. Okay, so we talked about that last time, and all that was in the context of the so-called transport theorem. This is the theorem that relates the motion of one reference frame to another. Or specifically, it allows us to take a vector derivative in one reference frame and equate it to a vector derivative in another reference frame. And that's really useful in the case of spacecraft engineering because we usually measure phenomena in a body fixed reference frame. Right? We usually measure angular velocity with a gyroscope that's fixed to the body. Or we might measure the angular momentum vector, or not measure, but we might detect it through knowing the mass properties and knowing the angular velocity vector. We might measure the magnetic field of the Earth through a sensor embedded or fixed in the body. And yet we also care about the orientation of these spacecraft in the inertial frame, so being able to relate these things is critically important. It's also important to get it right. It's important to get right the distinction between vector derivatives and simply the change in some numbers. So when we're doing all these derivations that have to do with vector derivatives, what we're really doing is working up a kind of set of algebraic rules that allow us to relate all the kinematics across multiple frames. Eventually, we will get down to using numbers for things. But until we get those kinematics right, it's not going to make a lot of sense to plug in some numbers. All right, and then the last thing we did was vector derivatives of a general variety. Okay, so this time, it's all about direction cosine matrices and the special orthogonal group of 3x3 matrices. And that really is the direction cosine matrix algebraic group. So don't worry too much about the group business, the fact that there's some kind of deep mathematics behind it. I'll talk about that a little bit. I think it's interesting. I think some of you will get a kick out of it. But in fact, it's not strictly useful for being able to apply these things in practice. It is good to know, though, that there are some fairly rigorous mathematics underlying it, and I'll give you a few references to look at if you are so inclined. So we'll talk about the direction cosine matrices, the special orthogonal group of 3x3 matrices, and attitude representations in general. So a direction cosine matrix is an attitude representation, but so are other things. So we'll talk about those other things as well. Now, we care about this, as I said, because we care about the attitude of the spacecraft in an inertial frame, right? But we might care about lots of other things. We might care about the orientation of a sensor relative to the spacecraft, and that sensor might be moving relative to the spacecraft because it's on a robotic arm, or maybe it's on a platform that's jittering somehow. There's a lot of reasons why we care about being careful among all these different frames. So let me summarize what we talked about before. We have a direction cosine matrix that relates the A coordinates to the B coordinates. And the way we're writing this here is direction cosine matrix Q allows us to map from a vector whose components are realized in the A coordinates to a vector whose components are realized in the B coordinates. So it's the same vector completely. The vector itself is independent of how we happen to cock our head when we look at it. And the direction cosine matrix is kind of like, a relationship between how our head is oriented and the vector itself. So since your cocking your head does not change the vector itself is sort of a constant in all this stuff. All the direction cosine matrix is telling us is how we are tilted when we're looking at this same thing. And that's why we think of this direction cosine matrix Q from A to B as being the thing that relates the representation of the vector in A to the representation of the vector in B. Same vector, different representations. So one way that we could write this is using the idea of a vectrix. I think we've talked about that a couple times. B1, B2, B3, these are basis vectors, a 3x1 stack of those things, called an array if you like, but really we will use the terminology vectrix to describe this. It's a matrix of vectors. Let's dot that with A1, A2, A3. A1, A2, A3 are basis vectors that are fixed within the A reference frame. Okay, so that outer product looking thing, that's a 3x1 matrix times a 1x3 matrix, should give us a 3x3, and it does. And the 3x3 matrix is this: B1.A1, B1.A2, B1.A3, and so on. I'll just write down the components here once, and I hope I won't have to write them again. So this is not a symmetric matrix. It's a 3x3 matrix, and even though the components themselves are unit vectors, there's nothing about this as symmetric in any sense. So on the diagonal you have B1.A1, B2.A2, B3.A3, and then everywhere else in the off diagonals you have, for example, B1.A2 in the 1, 2 cell or location of this matrix, using the standard way of numbering these things where we're talking about the row number followed by the column number. So row number 1, column number 2 is entry 1, 2, and that's B1.A2. Now each of these dot products, is associated with a cosine, right? If I took B1.A2 as an example, B1.A2, I'll write it down here, B1.A2 is the cosine of the angle between, we'll call it phi, between 1 and 2. That is, between B1 and A2. I could keep writing these dot products down, these cosines down, put them in a matrix of 9 entries, this 3x3 matrix of 9 entries, and I would have a matrix of cosines that describe the direction of one set of basis vectors relative to the other. And that's why they call it a direction cosine matrix. It's a matrix full of dot products that might as well be cosines. In fact, you could write them as cosines if you wanted to. So it's sufficient to come up with a direction cosine matrix using just the angles among all these different vectors. But that's not really how we generally do it. Right now I'm giving you a definition, a kind of statement that this is how this is all put together, but there's lots of other ways where we will calculate things and use them as well. So remember, we're talking about the direction cosine matrix Q that takes A into B, such that some arbitrary vector V that I've represented in the B coordinate system is direction cosine matrix from A to B times that vector written in the A coordinates. So that's what I've written right here. This equation here says V written in B coordinates equals Q from A to B times the vector V written in A coordinates. Now this is a matrix expression. So 3x1 matrix equals a 3x3 times a 3x1. We started this whole thing off talking about vectrices and vectors, and that's perfectly legitimate. And all we've done is go from the vector world to the scalar world, starting with vectrices and multiplying to get a 3x3 matrix. That 3x3 matrix allows us to do some algebra in the world of matrices and arrays. So once again, let me stress that V here, as written, has no little underline, which means it's not a vector, it's a matrix. It's an array of 3 numbers in a vertical stack. All right, and remember, of course, that in general, the representation of the vector in B is not equal to the representation of the vector in A, even though that vector V is one thing. But we're looking at it from 2 different perspectives. It would only be equal in a very special example, in a special circumstance. So let me go to the audience and say, what would that circumstance be? Right, when the direction cosine matrix is the identity matrix. And that would be the case where the direction cosine matrix represented no rotation whatsoever, or if you like, a rotation of 2 pi times n radians. In other words, you rotate it fully around. There's also another circumstance in which this would be true. What would that be? Yeah, that's it. So that's when the rotation itself happens to be around the vector itself. So even though the direction cosine matrix might not be the identity matrix, that is, it might not be a stack of a diagonal matrix of ones, it could still not change the representation of that vector if it happens to be that that single vector is also along a kind of axis of rotation that relates the A coordinates to the B coordinates. So we'll see how that pans out in a second. This has to do with what's called Euler's theorem. Anyway, those are two situations, or special circumstances, in which the vector v as written in A might actually be the same as the vector as v as written in A. So not equal in general. And this is why we have to use vectors to talk about vectors, and we have to talk about matrices using matrices. So let me remind you of another little trick of direction cosine matrix. We have this direction cosine matrix from A to B. If I wanted to invert that matrix, in other words, if I wanted to turn it into the direction cosine matrix that takes us from B to A, I'm writing that as a matrix inverse there. The little -1 means a matrix inverse. Well, it turns out all I have to do is transpose that matrix. It's convenient, right? Let me give you a quick example of what I mean by transpose that matrix. So let's say we have the direction cosine matrix B from Q to A, Q from A to B, and let's say it's something like this. Say we have A, these are still numbers, okay, so let's call something else. Let's say G, H, and I in the diagonal. Then I have, oh, I don't know, J and -J there. Okay? There's a direction cosine matrix for you. The inverse of that would be direction cosine matrix from B to A. And that's the transpose of the direction cosine matrix from A to B. And that would simply be diagonal is the same, but I swap everything across the diagonal. So I take the -J that's in the 2, 1 location, I put it in the 1, 2 location. So now I have -J up there and J down here. I also swap all the other off-diagonal components, which in this case are 0, so it all looks the same. But this is now the transpose of that original matrix, and also the inverse of that original matrix. And that is hugely useful. It's useful if you're doing hand calculations, which generally you only do in class, or maybe during some kind of theoretical exercise. It's also really useful if you're writing flight software, because now rather than going through all the calculations necessary to invert a matrix, which involves taking the adjoint or the cofactors and dividing by the determinant and all this kind of stuff, you just switch the little entries around in the matrix, and you're done. So in fact, you can make flight software much more numerically robust and also faster, just by recognizing this one little fact about the direction cosine matrix. Let alone it's easier on tests, so this is the way you should do it. All right, so a direction cosine matrix is a special kind of motion, or a special kind of relationship. It's a member of the special orthogonal group of 3x3 matrices. We call that SO3, S for special, O for orthogonal, 3 for 3x3 matrices. Or 3, if you like, for living in the world of R3. That it sort of has to do with the 3-ness that we associate with our vectors. This word special means something particular. It means that the determinant of the direction cosine matrix is exactly +1. In other words, not -1. Orthogonal means that each row is mutually perpendicular, each column is mutually perpendicular. And a special orthogonal matrix is actually what we also call proper orthogonal. It's a matrix, orthogonal, it's a matrix whose rows obey the right-hand rule. So that row 1 cross row 2 equals row 3. And column 1 cross column 2 equals column 3. And so on for all the permutations of the rows and columns. This right-handedness in the direction cosine matrix guarantees that what you get when you multiply the vector representation in one coordinate system by the direction cosine matrix is in fact a rotation, not something weird like a reflection, which might be the case if you had an improper orthogonal or a matrix with a -1 determinant. That would be a whole other kettle of fish. So we're only interested for now in these matrices that are special orthogonal or proper orthogonal with a determinant equals exactly 1. So this is a sanity check. If you ever find yourself creating a direction cosine matrix and wondering whether it's a legitimate one, all you have to do is take its determinant. Well, not all you have to do. One of the things you could do is to take its determinant and check, is it exactly equal to positive 1? If it is, then it's a good chance it's a legitimate direction cosine matrix. If not, it is not. If it's not negative, if it's not positive 1, you definitely don't have a legitimate direction cosine matrix. If it is positive 1, there may be some other issues, but for the most part, it's fine. Anyway, useful sanity check. You don't get +1, you got a problem. So there's some math that we could talk about here at this point. And I'm just going to reference you to the reading that's available on the Blackboard website. By a fellow named Stulpnagel, something like 40 years ago now, wrote this very clear and convenient article that describes this algebra, the algebra of rotations, in a way that clarifies what's at stake. This is an algebraic group, this group of special orthogonal matrices. And by algebraic group, I think many of you know, what we mean is that it's a set of matrices with certain specific properties. One of those properties is closure. And closure means that, in this case, closure under multiplication. It means that anytime you multiply two direction cosine matrices, you get a third direction cosine matrix. Direction cosine matrix. I'm going to write that down. Closure means Q from, let's say, A to B times Q from anything else, D to A, whatever it is, gives you a direction cosine matrix from D to B that is in this set, SO3. That sounds like a kind of esoteric point, but what it means is you're guaranteed that when you multiply direction cosine matrices together, you always have another legitimate direction cosine matrix. That's a very powerful tool as well. It gets you away from the need to sanity check the health of direction cosine matrices if you're just multiplying a few together. You never have to worry about that. Once you have direction cosine matrices, it's smooth sailing. Here's another one. There exists an identity matrix, or an identity, M-A-T-R-I-X. There exists an identity. In this case, it is, we'll write it as the number 1, and it's just 1s in the diagonal and 0s everywhere else. So this 3x3 matrix is the matrix that when you multiply it by another direction cosine matrix, you just get the same direction cosine matrix, or when you multiply it by a vector, you get that same vector back. And that identity is itself a member of SO3. In other words, this is a kind of direction cosine matrix. It's the direction cosine matrix associated with no rotation whatsoever. Okay, another couple of little factoids about this thing. There is an inverse. And we kind of already proved this in a way, but if you have an inverse multiplied by a direction cosine matrix or a member of SO3, you should get the identity. This is like saying that in just sort of straightforward algebra that we're familiar with, if you have the number 5, the inverse is 1/5. So 5 times 1/5 is 1. Same thing here. Q inverse times Q is 1. But in this case, it's the 3x3 identity matrix. And one more thing, so-called associativity. You know this for, again, the familiar algebra of real numbers. It's true here as well. Associativity here means if I have one direction cosine matrix, let's say from A to B, and another direction cosine matrix from C to A, it doesn't really matter what they are, multiply that by yet another direction cosine matrix from, I don't know, D to C, that I could change the parentheses around and end up with this, and it's still completely the same answer. I can group or collect on there, something like that. I can collect on any of these things. The order of operations doesn't matter. So, order of operations doesn't matter. All right, so anyway, the Stolt-Nagel reading says a lot more. It also talks about how many parameters are necessary to fully describe rotation. We're going to talk about that next. We're going to talk about the fact that really rotation is a three-dimensional thing. And that's why the special orthogonal group of 3x3 matrices, SO3, has a 3 in it. It takes you 3 parameters to fully describe rotation. But here's the problem. 3 parameters describe rotation, but that's kind of an ambiguous set of 3 parameters. In other words, it's not any 3 parameters that we can conveniently define. The mathematics of this says you should need 3 pieces of information to describe a rotation. That much is true. But there's no single 3-parameter set that actually does the trick for you all the time. And this is what gets a little bit tedious. And this is why we have to go to extraordinary means to talk about rotation. I'll give you the example of the direction cosine matrix. A DCM has 9 parameters in it. It has 9 individual scalar numbers in a 3x3 matrix. So that 9-parameter additive representation turns out to work just fine if you feel like carrying around 9 numbers with you. But it's actually 9 numbers with 6 constraints. So, for example, direction cosine matrix has 9 parameters, 6 constraints. Those constraints are that it's proper orthogonal. In other words, the dot product of all the rows is 0, the dot product of all the columns is 0, it's right-handed, and so forth. So those 9 constraints kind of give you the unitary direction cosine matrix we're thinking of. And that makes it kind of a headache. So if you were to try to estimate a direction cosine matrix, you'd have to take into account the fact that these constraints all have to be satisfied for any estimate of the directions, for the additive that you have. So direction cosine matrices, they're becoming sort of more popular as a way of parameterizing rotation, but still these days there are more convenient ways that we typically go by. We're going to talk about those. So we're going to talk about it through something called Euler's theorem. It says that the most general displacement of a body with one fixed point is a rotation about a single axis through that point. So that's one way of saying that you can always rotate a body around some axis by some angle to achieve any orientation. When Euler talks about the most general displacement of a body with one fixed point, he's talking about rotations. Because if you fix one point, that eliminates the possibility of translation. It's like a 3-dimensional pin, right? A sort of pin joint. You can't translate that one point. And so really anything you need to know, you can know about the rotation of the body around that pinned point. And that's, rotations. So we're going to talk about parameterizing rotations in terms of Euler's theorem to begin with here. It gives us some useful insights. We're going to define a rotation angle phi, and then a rotation axis we'll call it A, writing it as a vector. And if we have 2 coordinate systems, let's say A and B, and we're trying to talk about rotating from one representation into the other, we might write down A as an axis that lives in those basis vectors. In other words, we can write down that vector in terms of its representation in A or in B. And it turns out, in this particular case, this rare case, that the expression or the numbers we use to write down A in the capital A coordinate system are the same as we use to write down a little a in the capital B coordinate system. And that's because A is the axis of rotation. This is one of those 2 special cases that we talked about earlier. This is one of those cases where the rotation matrix is special. It's a rotation around this very axis. So when we try to write this axis down into 2 coordinate systems, we get the same result. If you follow me. All right, so we have a rotation angle phi and a rotation axis A, and Euler's theorem says that we can always write down, or we can always express the orientation of a rigid body in terms of some single rotation around a single axis about some with some single angle phi. So that's what the name of the game is right now. Let me write that down a little bit more algebraically. So let's say we have our axis A and the B coordinates, and we have the direction cosine matrix Q from A to B. If we wrote down that axis A in the capital A coordinate system, this expression here is a general expression. It tells us how you would, in general, translate from the A to the B coordinates. But here, this very special relationship gives us a unique kind of result. Does anyone recognize what this is? It's a special kind of problem. If I put the number 1 here, I don't know if that helps you, 1 times that axis. And remember we said the representation in B is equal to the representation in A. So really these are the same vector. So a vector equals a matrix times a vector. Is that familiar to somebody? Yes, it's an eigenvalue problem. Exactly right. So what this says is that little a is an eigenvector of the direction cosine matrix. That's awfully convenient. Furthermore, the eigenvalue associated with this eigenvector A, and there are other eigenvectors too, right? But the eigenvalue associated with this eigenvector is 1. In fact, positive 1. Because it's a, positive 1. So that's kind of a neat result, and we can prove that in a number of different ways. The other 2 eigenvalues, by the way, are e to the plus or minus I phi, where I is the square root of -1, the imaginary number. It's a so-called complex conjugate pair. Which is why we only have real numbers in the direction cosine matrix. Even though there's an imaginary number here, e to the I theta, you may remember as being part of Euler's formula. Yeah, Euler's everywhere in this particular story. Euler's formula is this. E to the I phi, some angle, right, is cosine phi plus I sine phi. And we normally associate that with the unit circle. Okay, so complex conjugate pair. Deal is that complex conjugate pair, when you multiply all 3 of these things together, the complex conjugate pair and the number 1, you get exactly 1. You may remember that the product of all 3 eigenvalues is the determinant of the matrix. So that's the number 1. Anyway, Euler's formula per se isn't a big deal here. I just want to sort of remind you that that's the scalar version of what we're about to see in 3 dimensions. So if you imagine the real axis and the imaginary axis here, and then this angle phi as kind of the rotation in the real imaginary plane, that's what you learned before as Euler's formula. We're going to be looking at a 3D version of that, which is extended a little bit. So let's take a look at that. That's for a single scalar rotation phi. We'll do a MATLAB example here. I'll put this on the Blackboard side. Unfortunately, I don't have MATLAB working on this computer at the moment. Let's take a look at this situation here. Let's say we have basis vectors little a1, little a2, little a3. Let's not confuse these basis vectors a1, 2, 3 with the axis of rotation. Same letter, I suppose, totally different deal, totally different nomenclature. We have b1, b2, and then b3. All right, so these are basis vectors, b1, b2, b3, a1, a2, a3. The deal is, how do you rotate from one to the other? Or, if you like, how do we write down the direction cosine matrix that expresses how a vector would be coordinatized in terms of the a basis vectors versus how it would be coordinatized in terms of the b basis vectors? And again, we're talking about a situation like this, where the b coordinates version of v is rotation q from a to b times v written in A. Now if you look at this here, and think about this as a rotation, so that we're rotating around the B3 axis, which is also equal to the A3 axis, because nothing is, since we're rotating exactly around B3, and assume that these three coordinates, three basis vector sets, one more time. Let's say that these three basis vectors, A1, A2, A3, are parallel to B1, B2, B3 initially, and we rotate from the initial position to the next position by that angle phi. Okay, we're rotating around the axis B3. So that is our axis of rotation, little a, as we defined it in general. Okay, so I could write down any one of these basis vectors in terms of any of the others. So cosine of this angle phi times b1 minus sine of that angle phi times b2. How did I get that? Well, I just kind of look at the picture here. I look at the fact that a1 and b1 are related. They're very close to each other when that angle phi is small, so they're related by a cosine. This works well for rotations that are simple like this, around one axis, like the A3 or B3 axis. When it's three-dimensional ones, it's a little bit nastier, but just for now, just to work out this example, look carefully and you'll see that as I rotate from A1 toward B1 around that axis, around the three axis using right-hand rule, the relationship between B1 and A1 is due to a cosine. If phi goes to 0, then B1 exactly equals A1. In other words, A1 is equal to cosine phi, which is 1 times B1, or A1 equals B1. Right? That's the situation with phi being a small number, or 0. And then as phi gets bigger, you get that cosine sort of relationship. So A1 is cosine phi times B1 minus sine phi times B2. A2, we can do the same thing. A3, we already know that that's equal to B3. Let me write that again for you. So that finally, we get direction cosine matrix from A to B as cosine phi sine phi 0 minus sine phi cosine phi 0, 0, 0, 1. And if you like, you want to do this in MATLAB, you could write it like this. Let's just define a variable BQA that looks like our notation for rotation from A to B. Let's call that variable this cosine of phi sine of phi 0 semicolon minus sine of phi. You could write this all in one line. It's just I can't fit everything on this little screen here, so I'm wrapping it around. Cosine of phi 0 semicolon 0, 0, 1 semicolon, close the brackets, we'll suppress the output with another semicolon there. That gives us a direction cosine matrix. Before then, we have to define an angle. So phi, the variable, equals, let's say, 0.1. That'd be 0.1 radians. Okay, so 0.1 radians, and then this code down here at the bottom gives us the MATLAB 3x3 matrix, a direction cosine matrix based on that. So here's some cool things we could do. We could calculate the eigenvalues, eigenvectors. Say v comma d equals eigen of this variable we just created, BQA. We will get a matrix V, which is a diagonal matrix. One of those entries is 1. Two of the others are complex conjugate pairs, or is a complex conjugate pair. And then we get the eigenvectors. You'll notice that one of them is exactly 0, 0, 1, and that is the axis of rotation. The other one is, the eigenvalue for that is the number 1. The other two are just orthogonal to that. We can also calculate the angle of rotation if you want by a tan 2 of the imaginary part of one of those eigenvalues, for example, d11, and parentheses, and real d11. Type that in, you get, ignore this little thing here. that gives us 0.1. In other words, you can figure out the angular rotation from that complex conjugate pair if you want to. Rotation axis is 0, 0, 1. So try that out. That MATLAB code will get you an example of how to manipulate these things in a numerical environment. But that's a simple example. Now, how do we get this in general? So in general, here's the formula, known as Euler's formula again. It is cosine phi times the 3 by 3 identity matrix plus the quantity 1 minus cosine phi times A transpose minus sine phi times this quantity here, A with a superscript cross. Remember what that is? We have A is 3 numbers like 1, 2, 3. Now in this case it's not a unit vector, I'm just putting in there so we can construct the cross product matrix and you see what I'm talking about. 0 is in the diagonal, minus the third component, plus the second component, minus the first component, plus the first component, minus the second component, plus the third component. That's a 3 by 3 matrix that gives you the matrix equivalent of the cross product. That little superscript x is not raising a to the x power, it's just a notation. I could put a tilde up there, I could put it in brackets. Some people do both of those things. But in any case, that's the way we can calculate the direction cosine matrix in general. We've got this A cross thing in there. Let's look at this one, A transpose. So remember, A is just our 3 by 1 matrix that represents the rotation axis in either the A or the B coordinate system, since it's the same in both ways. Okay, so A transpose is a 3 by 3 matrix. This is a 3 by 3 matrix. And we have these scalars multiplying these 3 by 3 matrices. You'll notice that only A cross is not symmetric. In fact, it's so-called skew symmetric. Skew symmetry refers to the case where you have the same magnitude of values across the diagonal, but different signs. Okay, so in this case, this minus 3, for example, is opposite across the diagonal from the plus 3, and the plus 2 is opposite the minus 2, the minus 1 opposite the plus 1. It's skew symmetric. Anyway, only that skew symmetric matrix is not strictly symmetric, which means the direction cosine matrix is almost a symmetric matrix. It wants to be a symmetric matrix, except for this cross product thing. And in fact, unless you have a 0 spin axis or a 0 rotation axis, there's always some asymmetry. So that's an interesting little fact. In other words, you don't get a symmetric direction cosine matrix unless it's no rotation at all. And that would be the identity matrix. All right, so that's how we get that in general. This formula here, super convenient, really powerful, and a little difficult to manage, I suppose, if you're trying to do some algebra with it. But there's a lot that comes out of this here. So I'm going to reference you to Peter Hughes's book, Chapter 2. This is one of the optional books for the course. I'll put a few pages of this on Blackboard so you can take a look at this. The Hughes reading really goes into a great deal of detail, provides very good insight into how this whole skew symmetric thing works and how Euler's formula for rotation works in general, again, for the three-dimensional case. Let's take a look at what the MATLAB code for this would be. So in MATLAB, we have, once again, BQA is our little variable that we're creating, which represents the direction cosine matrix. We could calculate cosine of phi times I3. That's the 3 by 3 identity matrix in MATLAB. You could generate it in other ways, but this is a cute way to do it. So I3, where were we? Plus 1 minus cosine of phi times A dot parenthesis, or dot apostrophe. We could also write transpose of A, but this is the way to transpose the matrix. It is literally a transpose. You could also just use the apostrophe, but that gives the Hermitian, which is sort of the complex conjugate transpose, and that's not exactly what you want in general, so just for precision, we'll use this. Minus sine phi times something else, CRS of A. So CRS on Blackboard. This is a function that I wrote that gives you that 3x3 cross product matrix. You can write your own, it's not very difficult. I wish that MATLAB had one. You can actually create an expression that gives you that, but it's very long and gnarly and not really convenient. So CRSA actually is a little bit more convenient. Anyway, that MATLAB code will allow you to generate the direction cosine matrix from the axis of rotation A and the angle of rotation phi. But there's also a cooler way to do it. And I love this. Let's have the direction cosine matrix again from A to B. It's e to the minus phi times A cross. So this is a so-called matrix exponential. If any of you have taken the linear systems class, you probably have seen this matrix exponential. We use this to describe the general solution to a time domain set of equations that describe the second order and first order systems in that particular class. It's a really useful trick. Sometimes that matrix that we're raising e to is the state matrix for an entire linear system. In this case, it's simply a 3x3 matrix. And it looks like this. Remember, it's a skew-symmetric matrix. We have, instead of the -3 component, we have a plus here because it's minus in the equation. Where is it? Right there. So let's say that we have A is A1, A2, A3, not to be confused with the basis vectors. These are just scalar numbers. 3x1 matrix of scalar numbers. So phi times mu. One more time, make this a little bit clearer. Okay. All right, so 0. Positive phi times A3, which is the third component of the axis of rotation, as written in B coordinates. You could also use the A coordinates version. It's the same thing. I'm just writing here as B to have a specific thing to write down for you. Minus phi A2, and then plus, right here, phi A1, and then the negatives of these off the across the diagonal because it's skew symmetric. Plus phi A2 minus phi A1. So that is that minus phi A cross matrix, a 3x3 matrix. How do you actually raise the single scalar e to a matrix power? Well, if you haven't seen it before, it looks a little bit weird. But it's a straightforward, well-defined mathematical operation. You can just do it. Conveniently, in MATLAB, there's a function for it. So let's use that, why don't we? And here's the MATLAB code for getting the direction cosine matrix from a matrix exponential. It's BQA equals EXPM. This is the matrix exponential now, raising e to the matrix minus cross A times phi. All right, so that's the matrix, the MATLAB way of getting this direction cosine matrix. There's a lot more that we can do to mess with MATLAB in this context. Let's move on to talking about this matrix exponential a little bit more because it gives us a lot of insight into other ways to think about the direction cosine matrix. Remember that if we had e to the x, just any x power, not to be confused with the cross product matrix, just e to some variable x. You know what, let's not even call it x. Someone's going to freak out about that. Let's make it e to the, oh, I don't know, how about the k power? There we go. E to the k power is 1 plus k plus 1/2 k squared plus 1/6 k to the third power plus 1/24 k to the fourth power plus a whole bunch of other stuff, right? This is one of these series expansions that you've seen ad infinitum in your undergraduate careers. Well, same deal for the matrix exponential. In this case, e to the minus phi a cross is 3x3 identity matrix, minus now, because of the minus sign, phi a cross, plus a whole bunch of other terms in various powers of the a cross matrix. All right, but we don't actually want to go that far. For right now, we're interested in this simple small angle approximation. Okay, going back one slide, you see how we had this 3x3 matrix here, that minus phi a cross, and there's zeros in the diagonal? Okay, that's this part right here. That is actually one of the terms in this expression we just wrote down. So in fact, if you already have phi and a, you could get a pretty close approximation of the direction cosine matrix for small angles just by also adding the identity matrix to that. So it looks like this. E to the minus phi a cross is approximately equal to 1's on the diagonal, and then phi a3, phi a2, phi a1, and so forth. So this is an approximation for the direction cosine matrix. When you have a small angle, it's good. The value phi, when the value phi is small, it's good. Now the axis A doesn't really come into play in terms of small and large. It's just a unit vector. Alternatively, you could write it this way. We could let now a matrix phi, a 3x1 matrix of values, be equal to phi a1, phi a2, phi a3, or maybe just for simplicity, call that phi1, phi2, phi3. And now we could write this matrix exponential. Are we doing A to B here? Yes. It's approximately equal to 1's in the diagonal, minus phi3, phi2, minus phi1, phi1 minus phi2, phi3. Cool thing about this is that these are phi are the small angle rotations about each orthogonal basis vector. So if I start off with the A coordinate system and I'm interested in how it's related to the B coordinate system, if there's a little bit of rotation around each axis, doesn't have to be, not a large angle, okay, but a little tiny bit. What this says is that those different axes are kind of decoupled from each other, and I can get everything I need out of a direction cosine matrix that assumes that they're decoupled. The thing is, in general, they're not decoupled. In general, a large angle rotation means I can't simply describe this with three little numbers like that. I've got to use something else. I've got to use, well, the 3x3 direction cosine matrix, which has 9 numbers in it. It takes me 9 numbers through a direction cosine approach to get what we want. But this gets us to where we want to really be thinking about what's the best way to represent rotation. I mean, all these manipulations are all well and good. They're useful to have. But if we need to carry some numbers around in our pocket to use to describe the rotation from one coordinate system to the next, what do we use? I will give you some options. You could use the direction cosine matrix, which has 9 parameters. You could also use the axis angle parameterization, which is 4 parameters, right? So that's phi and a, which is 4 parameters. You could also use 3 angles, known as Euler angles. We'll talk about them in a second. Or we could use 4 quaternion components. All right, so each of these has their value, their uses. The direction cosine matrix is great to have because ultimately you're probably going to be multiplying things in your flight code, your flight software, by the direction cosine matrix. So it's nice to have that. Do you really want to carry 9 parameters around, or would you rather calculate that when you need it? That's a good question. You could use the axis angle parameterization, in other words, carrying on the angle phi and the axis a, but there are several issues there. One of them has to do with as that attitude changes, you might find yourself changing one of those parameters really, really quickly, like the angle phi or the axis a. For example, as the angle phi goes to 0 and you sort of have no rotation, what is the angle around the axis around which no rotation happens? Doesn't make a lot of sense, right? So if you have a little tiny perturbation of an attitude, and then you go to some other little tiny perturbation, the change in the axis of rotation could be a really huge number. And very large, fast changes in numerical values are kind of bad news for flight software, for any kind of numerical integration or numerical system. So we'd like to move away from a system, parameterization like that, where the change in any of the parameters is particularly fast, or at least faster than really it should have to be, given how slowly the attitude might be changing. A very small change in attitude shouldn't cause large changes in the numerical representation of it. Right? So we'd like our numerical representation of that to be something kind of under control. So Euler angles, does that offer us anything better? Well, maybe. Here's what Stueltnagel says. It says that you can't embed, put that in quotes, you can't embed SO3, that direction cosine matrix special orthogonal group, in our 3-dimensional world. This is kind of awkward. The analogous problem is, what if you had a globe, like a spherical surface that we associate with the Earth, and you had to try to describe XY coordinates on there? All right, you've seen what happens when we try to do this. You take a globe, the globe is all well and good. You think of the globe as being a 3-dimensional object, but actually it's 2-dimensional. It's the surface of that sphere that actually matters, right? In fact, the surface of the ball. The sphere itself is the surface of a solid ball. That sphere is a flat thing. It's a 2-dimensional thing. It might not look flat to us because it kind of lives in 3 dimensions, but you could sort of peel the skin off of the globe and flatten it out somehow on a surface. But you maybe have tried this. Let's say you peel an orange or peel an apple. You always end up with a problem. And that problem could take the form of, you kind of have to rip that sphere somehow to flatten it out. You've got to tear pieces apart. You have discontinuities. Or maybe you have to stretch it in a weird way. So the Mercator projection that we're used to seeing for a globe takes the surface of the Earth, and the north and south poles end up stretched out from an infinitesimal point into a finite length. And that's, fundamentally, mathematically, a problem. What that makes the world look like is as if the United States is much bigger than it really is, that Greenland is huge, that Antarctica is immense down there in the South Pole. They're really not that big. It's just a result of taking a sphere and warping it onto a rectangular sort of surface, a projection. Anyway, the same thing that happens there for trying to map a 2-dimensional sphere onto a 2-dimensional flat plane is what Stueltnagel is talking about when we try to map the 3-dimensional world of rotations onto a 3-dimensional 3-parameter attitude representation. So you could use roll pitch yaw angles, Euler angles, which we'll talk about. If you used that, you would always encounter some kind of problem, some kind of ambiguity or singularity or some other kind of problem. You can read the Stueltnagel article to try to get that. It's a little mathematical. I'm sorry about that. Here are the problems you run into. Basically, no 3-parameter attitude representation is unambiguous, non-singular, and global. Okay, unambiguous means that we want the three-parameter attitude representation to give us only one attitude, not 2 or 10 or a million. That seems like not too much to ask, right? Okay, non-singular means that as that attitude changes, the attitude representation shouldn't undergo some kind of discontinuity or some infinitely fast change compared to the dynamics of the problem. Global means, global means that we want these three-parameter attitude representations to describe all possible attitudes, not just a small subset of them. So, in that context, let's think about these Euler angles. Named after Euler, a good idea. We'll get there eventually. Okay, an Euler angle sequence. It's typically for aircraft, sometimes for robotic systems. But you should not use them for spacecraft, or frankly anything that undergoes rotations of more than 360 degrees around some given axis. You will almost certainly run into one of the problem being a singularity. All right, so these Euler angle sequences look like this. You define 3 sets of basis vectors. So already this is going to be kind of complicated. So we have the A's, the B's, the C's, and by the way, I guess we'll define a fourth, which is the D's, J, K, L, I suppose we have L. We want to go from one to the other, so there's 3 steps involved. So we go across 3 pairs, and that I guess involves 4 sets of basis vectors. But it's really 3 rotations. So you define 4 sets of basis vectors, but really 1 axis of rotation for each set, and a specific order. For example, a 1, 2, 3 rotation would mean rotate around D1, then C2, and then B3, for example. Or maybe a 3, 1, 3 rotation. Rotate around D3, then about C1, then about B3. Each time you perform one of these rotations, the relationship of all these of all the basis vectors changes. And so you rotate around the original 3 axis, then you rotate around the new C1 axis, and then around the even newer B3 axis. You can see this is a little bit complicated, right? Let's do an example. You'll see what happens. During this sequence, you'll end up with a set of rotations. So let's say we're going to go from A to D, okay? So the mathematics of the multiplication, that's sort of the easy part. We're going to have a rotation from C to D multiplied by a rotation from B to C, multiplied by a rotation from A to B. A to B, B to C, C to D. All right, that's the sequence. So the first rotation gives us, let me sure this is the right answer here. Yes. Yes, it is. Okay, first rotation gives us A to B. Second rotation gives us B to C. Third rotation gives us C to D. All right, here's a picture that tells us what we're talking about. Let's hope I can draw this in the space we have here. All right, let's start with A1, A2, A3. For this particular sequence, we're going to first rotate around the A3, which equals B3 axis. It gives us a new set of B basis vectors. Those new B basis vectors now look like this. Here's B1 after the rotation. Let's see, B2. B3 is up there. Okay, another one involves the C axis. So here's C3. So we'll call these thetas, okay? The Euler angle is going to be theta, theta 1, theta 2, theta 3. Theta 1 takes us from D into C. Theta 2 takes us from C to B. And there's, let's see, another one over here. D1, C1. These are equal. Let me write them that way. Okay. Probably best if I just draw this picture and talk through it. All right, so then one more left. Let's see. Oops. Okay, here's how it looks. We start out at first with theta 1. That's a 3 over there. There we go. Okay, so theta 1 is about the D1 or C1 axis. That's right here. So I'm going to rotate right-hand rule around D1, which equals C1, and I get D2 to displace up here toward C2. So now that moves our reference, which is C at this point, up there. That same rotation around C1 or D1 moves D3 towards C3 in that direction. So now our new reference is the C-axis. Now that we're living in the C-axis, we do another rotation. We rotate around C2, which is right here, by the angle theta 2. So you see what happens? Theta 2 moves from C3 over to B3. It moves C1 toward B1. And now our reference axes are the B-axes. The final rotation is around B3, which equals A3, right up there. Rotate right-hand rule wise around B3. That moves B1 into A1, or toward A1, I should say. Moves, where is B2 toward A2. So now our final set of axes is the A-axis. And if we start as D, end up as A, we can compute the Euler sequence like that. Here's how you actually compute that. So all that setup is really Byzantine and kind of irritating, but here's why it's sort of useful. The direction cosine matrices are really straightforward. I can write down any set of basis vectors in terms of the others, but through a very simple set of rotations. Let's take the B and the C relationship, B and the A relationship. So I have cosine theta 3, I'm going to simplify. Rather than writing COS, I'll write C. Rather than SIN, I'll write S, just so we can keep things a little bit short. So here's how that looks as a single axis rotation. This is the direction cosine matrix Q from A to B for this Euler sequence. And that rotates from the basis vectors in A to the basis vectors in B. I could also write down the direction cosine matrix for rotating from from B into C, and that one looks like this. equals cosine theta 2, 0, sine theta 2, 0, 1, 0, minus sine theta 2, 0, cosine theta 2. And so on for one more. We don't actually need the other one right now. This is kind of like the others. You'll notice this negative sign. That's the pattern for creating these Euler-style direction cosine matrices is you have cosine sines in a little sort of partition. Here we have the upper left partition, cosine, sine, sine, cosine. Here for y we have cosine, sine, sine, cosine. And then for the third one, I guess I'll just write it down here. It looks like this. Cosine theta 1, minus sine theta 1, sine theta 1, cosine theta 1. There we go. That's the direction cosine matrix for the 3 rotations. So this one was B to C, that's A to B. So this one is C to D. Anyway, the pattern here is this. You've got this partition, this 2 by 2 partition of cosines and sines. The only one is the 3 rotation and the 1 rotation look almost exactly the same. The skew symmetric part, the little negative sign thing, is in the upper right corner. It's only for the rotation on the second axis, or the y-axis, if you like, the second of the 3, where you have this negative sign down here. You can derive all these from first principles. You can work it all up by hand using that kind of trick of inspecting by small angles and right-hand rule. But this recipe here gives you everything you need to know about how to generate these Euler rotations. So if you define the sequence and know how to generate these 3 by 3 matrices, you multiply them all together and you get a big hairy mess of angles. Now, that all seems well and good, if a little bit tedious. But here's what happens. There's a singularity when we go to represent the angular velocity vector in the axes. Remember that we can write down the angular velocity vector of one frame with respect to another in terms of a very simple set of relationships. This is kind of analogous to how we do the multiplication for direction cosine matrices. It's just addition in the world of angular velocities. Even though additive can be a kind of complicated thing, this is the one area where things really are quite simple. How you figure out the angular velocity of one frame with respect to another, just add up all the frames in between. I mean, for additive, it's just multiplying all the frames in between, but maybe that's harder. I don't know. Anyway, this is how you write down the angular velocity of D relative to A. It requires these 3 angular velocities. And these are really straightforward. I could write them down as the following scalars. Theta 3 dot along the B3 axis, whatever that is, plus theta 2 dot along the D2 axis, plus theta 1 dot along the A1 axis. And by the way, I could just replace B3 with A3 and so forth, because remember, the axis of rotation would be the same in the 2 different frames. So I could swap them out if that was more convenient for me. But this is just one example. All right. So, where were we? Okay, so the singularity, right. If we take the derivative, we get something like this. Angular velocity of A relative to D is theta 1 dot plus cosine theta times cosine theta 2 sine theta 2 theta dot 2 times sine theta 3 B1 plus negative theta dot 1 cosine theta 2 sine theta 3 plus theta dot 2 cosine theta 3 along the B2 direction plus theta dot 1 sine theta 2 plus theta dot 3 in the B3 direction. And if you like, I could write that as 3 scalar components, each of which multiplies a corresponding basis vector that we associate with the B frame of reference, or B coordinate system. So omega 1, 2, 3 are three scalars. Anyway, that's how you would write this all down. And that's just results from a bunch of algebra that came from the direction cosine matrices. Very tedious, but I'm sure you could walk through all that stuff if you wanted to. Here's the point. Let's write this down as those scalars. I guess I used B before, but A, same thing. B and A, just different coordinate system, same physics. Here's a matrix relationship that comes from that expression I just wrote down. Okay. I'm going to point out to you that this matrix I just wrote in here, this maps from the world of theta dots into angular velocity components. This is not necessarily a DCM. It might be under some weird rare circumstance, but it's not in general a direction cosine matrix. It's just a thing that multiplies some numbers. Okay, don't take that. Even though it looks like a direction cosine matrix, it's not. Conveniently, though, that whole expression that we had back here, this is all linear in theta dot, which allows us to do this in the first place. So we can write a linear expression. That's at least sort of nice. But what if we wanted to figure out theta dot 1, theta dot 2, theta dot 3 as a function of the angular velocity components? Well, we would have to invert that 3 by 3 matrix. Now, unlike a direction cosine matrix, there is no guarantee that this inverse always exists. You know that the inverse of a direction cosine matrix exists because you can always transpose a matrix. And there's no singularity or weirdness associated with doing that. You just put the numbers in different places. You know you can do that. Here, however, when we invert this matrix, we can't just do that. We can't just transpose it. We have to go through all the other shenanigans of figuring out the inverse of the matrix. And you can plug it into MATLAB if you want, or God help you actually work through it yourself by hand. But here's what it looks like. 1 over cosine theta 2 times cosine theta 3 minus sine theta 3, 0. And cosine theta 2 sine theta 3 cosine theta 2 cosine theta 3, 0. Minus sine theta 2 cosine theta 3 sine theta 2 sine theta 3, 0 times these angular velocity components. All right, this is the problem, right? Thank you, strange interface. There we go. That's the problem. Problem is that denominator for certain values of theta goes to 0, right? Namely, theta is pi or 3 pi over 2 or some multiple like that. I'm sorry, pi over 2 or 3 pi over 2 and so forth. At those angles, the change in Euler angles with respect to time is infinitely fast. It may be only one of them that's infinitely fast. Maybe the others are 0 or something. Who knows? But at least one of them is going to hell in a handbasket because of this denominator here. So this divide by 0 kind of error results in the fact that you can't have a non-singular set of Euler angles. So you might ask, what if rather than using a 3-2-1 rotation, we did a 3-1-3 or a 2-1-2 or a 2-3-2 rotation? Doesn't matter. Any set of Euler angle orders that you use, any ordering of the Euler angles, always gives you some kind of singularity like this, so that you cannot use those parameters as dynamical variables for a system whose attitude dynamics are completely arbitrary. You can use them just fine, though, if you're talking about, let's say, a passenger jet, because we really don't expect 787 to do like a 360-degree roll, right? That's not popular for the ticket buyers. Or we don't expect it to pitch 180 degrees, also a bad thing for marketing purposes. So for that, in those circumstances, it's probably okay to use Euler angles. I mean, I'll tell you, if my aircraft ever were to roll 180 degrees or 360 degrees, I certainly wouldn't want the flight software to crap out at the same time as something else bad is happening. So in my opinion, you want to use mathematically sound parameters no matter what the circumstances. But you can get away with Euler angles in a lot of applications. You just can't get away with it for spacecraft, because in space, the rotations are kind of arbitrary. Rotating around the planet, you're pointing in all possible directions in that axis, It might be rolling arbitrarily far, it might be pitching arbitrarily far. So roll, pitch, yaw, 1, 2, 3, x, y, z, all those axes, however you want to define them, there's no way out of it. The spacecraft might be undergoing completely arbitrary motion, which means you have to have a non-singular additive representation. And all this effort we just went through with Euler angles was all to reach this one point, which is don't use Euler angles. Okay? So some of you got excited here. I'm not following what Professor Beck is saying. There's too much algebra here. Don't worry about it. This is meant to be evidence for you that you cannot, in fact, use these things the way you might want to. But I do have a way for you to get what you want, and that is the use of quaternions. So let's talk about the better choice. Stoltenagel agrees it's a better choice. Hughes agrees it's a better choice. And who am I to argue with that level of expertise? So the better choice, quaternions. A quaternion is a 4-parameter attitude representation. Q1, Q2, Q3, Q4. We're using little q's here. Its magnitude, or length, is exactly 1. Or if you like, I can calculate Q transpose Q, exactly equal to 1. How do we know this? Well, one way to think about the quaternion is you could imagine it's a result of an axis angle parameterization. The quaternion is actually very closely related to that axis angle parameterization. It looks like this. A1, A2, A3 times sine of the angle of rotation over 2. And in the fourth component, cosine of the angle of rotation over 2. I will pause briefly to point out that sometimes people call the first 3 numbers the vector part, and sometimes they call this the scalar part. This is not a vector, it's 3 numbers, as I've said about 20 different times in the class. It's just 4 numbers in a stack. This is one way in which you can map the axis angle representation into the quaternion world. It's not the only way. Now, how you define this order does matter. I mean, just like the direction cosine matrix, whatever columns or rows I put where, that determines whether I'm talking about the rotation from the 1 axis into the 2 axis or whatever. So it does matter. But what I'm saying is that there's nothing vector about this. This is just 4 numbers in a stack. And you'll sometimes find, certainly in very old-fashioned texts and a few academic institutions around the country, you'll find these 3 swapped with this one. Sometimes you find the cosine or scalar component up on top as Q1, and then the others are Q2, 3, 4. The convention I'm showing you here is the convention that is the most common. It's used in virtually all of the academic literature. It's used at Boeing and Lockheed and JPL, as far as I know. I cannot think of a single place it's used outside of a few academic institutions and also sometime in MATLAB. So if you are not careful and you use some of MATLAB's block sets, you will occasionally discover that the direction cosine matrix is defined in the weird old-fashioned backwards way. And yes, I'm being valuative when I say that. I think we should all agree on a standard and use it, and most people have. It's just that information has not yet propagated everywhere. So sadly, you gotta look carefully when you're using someone else's software, and be sure that you're not using the kind of backwards definition of the quaternion. But here's how it works. Let's define what I'm going to call Q1, 2, 3. It's just a quick way of writing it down as this first 3 components here. Again, it's a 4 by 1 matrix. This is a 3 by 1 matrix. And then Q4 is Q4. I'm going to point out to you that if I wanted to calculate Q transpose Q, that is, I could group things together. I get A transpose A times sine squared of phi over 2 plus cosine squared phi over 2. Well, A transpose A, remember A is a unit vector, that's just 1. Then I have sine squared plus cosine squared, that's 1. So Q transpose Q is 1, which is what we wanted in the first place. So in fact, that does equal 1 no matter what, by definition. Let's look at how these could be used for some benefit. We could calculate the direction cosine matrix, VQA, from rho Q. We have lots of options. Here's one. We could use the version of Euler's formula adapted to the quaternion. It looks like this. So Q4 squared times Q123 transpose Q123. Again, that's a 3 by 3 matrix. That's right. No, it's not at all. It's a scalar. All that times 3 by 3 identity matrix, plus 2 Q4 Q123 cross. That's pretty simple, right? I mean, given all the other junk we've seen lately, that's pretty simple. The factor of 2 there comes from that 1/2 in the calculation, right? The sine of phi over 2. Otherwise, I think you'll see it's almost exactly what we have for Euler's formula using the axis angle formula. It's really not much effort for you to verify that this is exactly the same thing, but just with that definition of quaternions instead. All right, no big deal. So far we're okay. Oh, wait, I'm sorry. I forgot a term. Plus 2 Q123 transpose. Sorry, that's the whole story. Right, 3 by 3 matrix there, 3 by 3 matrix there. There are lots of options for this. Here are some other neat little features. The quaternion derivative. Nil Q dot. This is extremely useful. Sounds esoteric. It's extremely useful for simulations. So soon enough we'll have a homework that involves MATLAB. You will have to write some code that takes the derivative, or actually integrates the derivative of a quaternion, and then that is the way that you propagate the equations of motion through time for an arbitrary situation where you require numerical differentiation or integration. Anyway, Q dot is 1/2 this matrix. Q4 minus Q3, Q2, Q3, Q4, minus Q1, Q2, Q1, Q4, minus Q1, minus Q2, minus Q3, times the angular velocity components. For the case of omega of A relative to B equals scalar omega 1 A1 plus omega 2 A2 plus omega 3 A3. All right, so this is really convenient. If you look at this, you'll see a couple of patterns emerging. One thing that you notice is Q4 on the diagonal, and then a skew symmetric Q1 through 3. That is no accident. The algebra of these rotations always gives you something that looks kind of like this. And then on the bottom here we have Q1, 2, 3 transpose, the negative of it. This is, a kind of fourth order version, if you like, a four-dimensional version of that skew symmetric matrix we wrote down for the direction cosine. Just FYI. Don't worry about it. Also, we could invert this, which is awfully nice. Unlike the case of Euler angles, you can always write this down because there's a linear relationship among all these things. We haven't got nonlinear cosines and whatever of the angles showing up. So this is just Q4, Q3, Q2, Q1, minus Q3, Q4, Q1, Q2, Q2, Q1, Q4, Q3. Just a transpose of that matrix times Q dot. Couldn't be simpler. I will point out that for those of you who want to take a look at the optional reading, this is in Hughes' table on page 31. Another neat thing that we can do is invert the quaternion. Now, what would that mean? Because the direction cosine matrix, the inverse is kind of a well-defined operation where you're just kind of inverting a matrix so that you can come up with the opposite version of the rotation, right? Either from A to B or B to A. Right? Well, what does the inverse of a quaternion mean? Well, it means the other direction of rotation, right? Rotating back. Just like the direction cosine matrix, it's just now we're not thinking of multiplying the DCM by something. This is just the quaternion itself. So inverting the quaternion is plus or minus Q1, 2, 3, Q4. Or if you like, it's Q1, 2, 3, and then minus Q4, or minus q1, 2, 3, q4. So what's going on here? There are two solutions for this? What? Yes, there are, and this has to do with the fact that a quaternion is non-singular, it's unambiguous, and it's global, which is exactly what we want, what Stuhlpnagel says we need. But it's also redundant. In fact, there's a whole shadow set, if you like, of quaternions that are kind of redundant to the first ones. I can take any quaternion and do this to it. I can take the opposite of the first three components, leaving the fourth alone, or take the opposite of the fourth, leaving the first three alone, and I get the same deal. In other words, minus q is the same as plus q. That's a weird thing. If you look at what's going on, it makes a little bit of sense. Let's take a look at the definition of the quaternion. If we look at the axis-angle relationship here, A123, that is some axis, right? And then sine of the angle, phi, right here. If I took the negative axis and the negative angle and threw it in here, I would get the negative of, I would get exactly the same thing in the same place. So if I take the negative quaternion components, I get exactly the same attitude. Because again, that sign multiplies out between these two guys. So that's kind of an interesting little feature. In other words, if I define an attitude, if I give you a direction cosine matrix Q, I get two quaternions. So if I were to ask you at a test or on a homework, what is, represent the direction cosine matrix here using a quaternion, you should give me two answers. You should give me the positive and the negative. This is kind of like having two roots of the square root, right? Square root of some number. There's two values, a positive and a negative number. In fact, the algebra is very closely related. If you look at how if you look at how Q shows up in here, Q is always quadratic, right? You're always multiplying components of Q, little q. So if I were to completely negate, that is, take the negative of every single quaternion component, all four of them, I would end up, that negative sign would fall out when I calculate the direction cosine matrix from that quaternion. Yet more proof that you can take a quaternion or its negative and end up with exactly the same direction cosine matrix, which means exactly the same attitude. And that's kind of a pain when you're doing flight software. So you have to decide what you're going to do here. And one thing that people sometimes do is always use the positive value in that fourth scalar component. It's one thing you could do. You could also sort of blow it off and not worry about it. But think about if you had a feedback control system and your goal is to go to a specific attitude. Okay, now if you turn that attitude into a quaternion to use in some kind of feedback control, if you're headed toward the positive quaternion, not realizing that mathematically it's the same as the negative quaternion, and the negative quaternion is actually closer in the sense of the numbers are closer to that, you could actually be rotating the long way around. This amounts to rotating around 360 degrees instead of rotating around 0 degrees. Or if you like, it's going 370 degrees instead of going negative 10, or something like that, or going 10. Anyway, it's a wraparound kind of a feature. Okay, so we've talked about derivatives, talked about inverses. One more attitude representation I want to throw out there at you. The so-called Rodriguez parameters. And there are different flavors of these things. The idea with the Rodriguez parameters is it tries to be as useful as a quaternion, but still only give you 3 components. And we'll see a little bit later when we do some feedback control that it's nice to have 3 components for 3 degrees of freedom. That is, you have roll, pitch, and yaw. You kind of would like to have 3 things to deal with rather than 4. So that's one motivation for this. To be honest, these are of more academic interest than practical interest, at least in my experience, but I will show them to you since they do come up from time to time. Let's write them down as rho, so the Greek letter R, not P, little rho. So rho I is Qi over Q4. And there are 3 of them, rho 1, rho 2, rho 3. And I could write that as A times tangent of phi over 2. Right? You get me? You guys remember the first 3 components of that quaternion? That's A1, A2, A3 times sine of the angle over 2, phi over 2. So if I divide sine of the angle over 2 by cosine of the angle over 2, I get tangent of the angle over 2. And that's exactly what we have here in the definition. That's all that is. It's not particularly profound. What you're doing, though, is reducing the 4-parameter set to a 3-parameter set. But because of the way these things work, that guarantees that this is now problematic. It's either singular or not global or discontinuous somehow. And which is it? Can you tell? Yeah, it is singular. It's singular because what happens when cosine of phi over 2 goes to 0? That would happen at the value of pi, right? Or multiples of pi. Well, that denominator goes to 0, which means the Rodriguez parameters blow up. Oh well. And so in that sense, it's not really much better than Euler angles. I will tell you it's a little better because you haven't got all that Byzantine complexity of, rotate around 1, then 2, and then 3, and then which order are you in. And, this is at least more simple to define, but it's no more robust, let's say, than Euler angles. So it doesn't really get you much farther. But just for completeness, I'm going to write down the direction cosine matrix in terms of the direction of the Rodriguez parameters. So Q is a function, big Q is a function of rho. It's this, 1 plus rho transpose rho times the quantity 1 minus rho transpose rho times the 3 by 3 identity plus 2 rho transpose minus 2 rho cross. And that's very similar to the direction cosine matrix as a function of little q, the quaternion. Alternatively, this is kind of cool. Let's define something called the Cayley transform, which, if you have not seen it yet, you will see it again in some graduate class somewhere. I'm going to define a 3 by 3 matrix R to be that rho cross. Then I can actually write down Q of rho as Q of that big matrix R, like this. 1 minus R, where this is the 3 by 3 identity matrix 1, times 1 plus R inverse, which, by the way, equals 1 plus R inverse times 1 minus R. That's really compact and convenient. It's very, very cool. And if you are particularly interested, let me know. There's an article by a guy named Panos Tsiotris who talks about how you can take Rodriguez parameters and extend them not just to look like a quaternion, but in fact to stretch them so they become non-singular later. Right now these become non-singular after a rotation of 4 pi degrees, or maybe 2 pi depending on the situation. Well, in the case of his so-called modified Rodriguez parameters, or higher order Rodriguez parameters, you can stretch out that region of applicability almost as far as you want, which is kind of cool. I mean, there's still a numerical singularity there, so it doesn't really avoid the fundamental problem, but still, it could be much more useful for other applications than just the Euler angles or just the Rodriguez parameters. And he uses this Cayley transform to good effect in that paper. So if you really want to get into that stuff, you let me know. I'd be glad to show you the reference, and you can learn more about it. We also talk a little bit about this in 606, which is the graduate class that has to do with attitude dynamics and control. But for now, that's where we are with attitude representations. Let me remind you what we did today. We talked about direction cosine matrices and some of their special features. We talked about how to invert them. We also talked about how they are related to the axis angle formulation. The axis angle formulation is one way to look at how rotations happen. It's a very convenient parameterization because it helps us understand things in terms of Euler's theorem. Euler's theorem says that you can rotate around any axis by any angle and produce some, let me say it this way, you can produce any orientation by a rotation about some axis and by some angle. Euler's theorem gets us to the point where we recognize we could, all we need is 3 parameters to parameterize rotation. But this fellow named Stulpnagel tells us that you really can't use 3 parameters. You have to use at least 4, maybe 5 or 6. And there are some other weirdly flavored 5 and 6 parameter attitude representations we haven't talked about. The direction cosine matrix is non-singular, but it has 9 numbers, so it's kind of inconvenient in that respect. The much more convenient one is a quaternion. The quaternion has 4 parameters in it. It is non-singular, it is global, it is unambiguous, but it's also redundant. As every parameter, every parameterization with more than 3 parameters has to be, because there's too much information. So there's always a constraint. In the case of a quaternion, it's Q transpose Q equals 1, and that's true for the direction cosine matrix as well. For the case of the quaternion, though, we have some very simple relationships between the angular velocity components and the derivative of the quaternion, which makes it particularly convenient for numerical integration. So it lends itself well to doing simulations. The Rodriguez parameters are yet another additive parameterization of some possible interest. It doesn't really avoid the singularity problems, but it can allow you to have a larger region of non-singular behavior, which could be useful for some situations. All right, so that was a rapid-fire run through the world of additive representations, and we'll talk more next time.